In this video we'll look at how to convert the Cartesian form of a complex number into what's known as the polar form. So the Cartesian form is in terms of the real and the imaginary component. So x being the real component and y being the imaginary. So let's call that complex number z. So I want to change that in terms of the angle theta here and in terms of the length of the complex number. And that will be our polar form. Now the angle theta here, we actually call that the argument of our complex number z, or abbreviated to argz. And we have to make sure that our angle of theta is in fact between negative pi and plus pi. And that just makes life a little bit easier because there are infinite possibilities for our angle of theta. Now if we consider the angle theta and look at its cosine, we have the cosine of theta is equal to the adjacent length, which is x, divided by the hypotenuse, which is the length of the complex number, and if the complex number is z, then the length is mod z. So to rearrange that to get x by itself, we end up with mod z times by the cos of theta as the x component. Do the same for the sine of the angle, and we get sine of theta is equal to the opposite length, so y divided by the length of the complex number. So once again, rearrange to get y by itself, and we end up with mod z times by the sine of theta. So the coordinates x and y can be expressed in terms of the angle and also the length of the complex number. So if we now consider point P, a point on a circle of radius r centered at the origin, then we know that the coordinates of point P, we would have length r times by cos theta, length r times by sine of theta. So the complex number z, which was x plus iy, would now be r cos theta plus I times by r sine theta. Take out a common factor of r, and we have z is equal to r times by cos theta plus I sine theta. So we can make a substitution there. The fact that the length of the complex number r is in fact mod z, and the expression cos of theta plus I sine, we can actually replace that by this abbreviation, cis of theta. So we end up with our complex number being now mod z times by cis theta. And that's known as the polar form of a complex number. So the Cartesian form of a complex number is x plus iy. The polar form of the complex number is now mod z times by the cis of theta. Once again, mod z is the modulus and theta is known as the argument. And once again, the abbreviation for cis theta is cos theta plus I sine theta. All right, let's convert these complex numbers into polar form. So first up, I'd recommend drawing a sketch. So if we have the real axis and the imaginary axis, now we have the complex number 2, which is in fact across here 2 units. So we know the length of the complex number is in fact equal to 2, and we have the angle, or the argument, is in fact equal to 0 in this case. So therefore we can express the number 2 in polar form as 2 times by the cis of the angle, or the argument of 0. Next one. So we have negative 4i. Let's graph that. So negative 4i will be down here, so negative 4. Right, so we know the length of that complex number is equal to positive 4 units, and the argument, and once again we start from 0 and work around to pi, or 0 and work around to negative pi. So in this case, the angle, or the argument, is around to here. So in this case, the arg of complex number z is in fact equal to negative 90 degrees. Expressed in radians, that's negative pi on 2. So therefore, our complex number of negative 4i can be expressed as 4 times by the cis of negative pi on 2. Let's look at the third example. So 3 plus 4i, so we have 3 on the real axis, we have 4 on the imaginary. So there is our complex number z. So to work out the length or the mod of z, we would have 3 squared plus 4 squared and take the square root. In fact, it's a 3, 4, 5 triangle, so the length is equal to 5. Now, what about the argument, that angle there? So if we consider a right angle triangle here, we know that the tangent of theta is equal to the opposite length, which is 4, divided by the adjacent 3, and therefore we end up with inverse tan of 4/3, and that will give us the argument. So using our calculator, we get approximately 0.927. So therefore we can rewrite 3 plus 4i in the form of 5, the length, times by the cis of 0.927. And that now is in polar form. Alright, last example, let's change polar form back into Cartesian form. So once again, I would recommend you draw a sketch of this situation. Now if the argument is 5 pi and 6, that puts us in the second quadrant over here, and the length is root 3 units. If we write root 3 cis 5 pi and 6 in its expanded form, we'd have root 3 times by the cos of 5 pi and 6 plus I sine of 5 pi on 6. So, what is the cosine of 5 pi and 6? We know we're over here, so it's a negative value for cosine, and we work out the cosine of pi on 6, we'll get root 3 on 2. So therefore, in that quadrant, we have negative root 3 on 2, and the sine of 5 pi on 6 would be positive 1/2. Once again, the sine is the y-coordinate, so I times by 1/2. So if we expand that, we'd end up with minus 3 on 2 plus I times by root 3 on 2. So now that is expressed in Cartesian form. So we've converted the polar form, this form up here, into our Cartesian form down here.